Okay, first let's have a look of this simulation over here. And we have object 1 and 2. So the center mass have been labeled for you as a cross. So you can tick over here if you want the center mass or not. So there's other things you can tick, you can try them. So what we want to do is right now we consider this is a two-dimensional situation because one dimensional is only going left and right. So let's look at one-dimensional situation. So you see the velocity of the center of mass before and after the collision actually don't change. Say here. So this thing, look at this thing, does not matter how this two does, as long as the total momentum is stay the same, then this velocity will stay the same. Okay, so let's have a look. Bang. See, this will stay the same. It does not matter what happened to these two, as long as the total momentum stays the same. Okay, so if we look at 2D situations, so same thing is gonna happen. So what I can do is I can restart it. So I can change the velocity, say it's gonna go in this direction. And then I'm gonna try to make it go this direction. Hopefully they're gonna hit each other, and look at the center of mass over here. Yeah, after the collision, see, this one's going this way, this one going this way, but this center of mass is still continuing going the original direction with the same speed. So I can restart it, and I can even using the pen as a reference, you can see how it's gonna go down at the same. You can see how this does not really change. Okay, so that is the center of mass situation with conservation of momentum. Okay, sweet. So now I'm gonna show you guys a question over here, and this question is quite difficult. So I want us to look at this question together. Okay, so let me just adjust my tripod. Okay, so let's have a look. So in the diagram A, B, and C, show the position every second. Okay, so we're gonna circle the keywords here is every second. Okay, so every second, let's have a look what's going on. Originally it was like this, right? We have A over here, and after 1 second, it moved to here. And then we took another picture, another second, it moved to here, okay? Of two ice skaters, okay? These two are ice skaters, father and daughter of mass 80. One is mass 80 and one is 40, okay? So we can say the big one is 80 and the small one is 40, respectively, as they glide together over the ice. At C, the father pushed the daughter forward so that she starts to move ahead of him. The daughter continues as shown. Okay, the daughter was moving 5 meter, 5 meter, and then bam, it moved to here. So we can actually figure out the daughter's speed over here. Okay, so I'm going to use a black pen. Over here, it moved 5 meter, 5 meter, 5 meter per second. So 5 meter per second, and then here 5 meter per second to here, and then this section over here it moved to 1 2 3 4 5 6 7 8 9. The daughter actually started traveling at 9 meter per second. Okay, and then let's read over here 1 2 3 4 5 6 7 8 9. Okay, so this is actually an explosion situation because originally the father and daughter are going together, and then together, and over here they push each other, so the daughter start to go faster. Okay, and we know if the daughter starts to go faster, the father is going to go slower, right, because of conservation of momentum. Okay, so first let's have a look. Calculate the speed of the system, the father daughter before separate. Before the separate, we can just read over here. Every second it travels at 5 meters, so I'm going to say this is just 5 meter per second. Okay, all right, so and then second one, put dots on the diagram to show the position of center of mass. So I want to find the position of center of mass of the system of the father and daughter each second before and after they separate. So label DEF, DEF. Okay, so A, where's the center of mass? Center of mass is just over here because the two things are together. So this is the center of mass. I'll use a red pen. Center of mass, it's gonna be here, it's gonna be over here. Okay, and that's when the two things is gonna separate. As we've seen from the simulation, the total momentum does not change. So that is why this will actually not change. The velocity of the center of mass will stay the same. So the velocity of center of mass is gonna be over here. So this is gonna be D. When the daughter travels to here, the center of mass is actually going to be here. Whereas E is going to be here another second, it's going to travel another 5, and then F is going to be over here. So you can see the daughter has gone ahead, but the center of mass is remaining the speed, where the father should slow down. Okay, all right. So let's have a little question D. Calculate the speed of the daughter and the father after they have separated. So speed of the daughter and the father after they have separated. Okay, now we can see the daughter is easy. So the daughter, we can already know it's going to be 9 meters per second just based on the graph we've read. It traveled to here. Okay, all right. And then we're going to use conservation momentum, try to calculate the father's speed. Okay, so let's try this. So momentum P before gonna equal to P after. So P before, I'm gonna be using M total times V center of mass equals to M father V father at M daughter V daughter. Okay, because this is a 1D situation, all of them are traveling this way, so I don't need to give it positive or negative because it's all going to be positive going downwards. Okay, and we don't need to use trigonometry because it's a 1D situation. All right, so let's put the numbers in here. So M total is going to be 120 times 5. It's going to equal to 5. Daughter is going ahead. Daughter is 40. So 40 times 9 meters per second. That's the new speed of daughter. That will be at the father's speed. Okay, all right. So let's put this in calculation. 600. 360 plus ATVF. Okay, so ATVF is going to equal to this minus this. That's going to become 240. So VF equals 240 divided by 80, which is giving me 3 meters per second. All right, so the dad is going to be traveling at 3 meters per second. Okay. Calculate the momentum of the system of father and daughter. Oh, we've actually already calculated, so it's just going to be 600, right? 600 kg meter per second. Here, okay. Calculate the momentum of the daughter and the father after they have separated. The momentum of the daughter, okay, the momentum of the daughter is 360 kg meter per second, and then the father will be 240. 240 meter per second. Okay, so at all time the momentum of the system is the same. The momentum is the addition of the momentums is the sum of the momentum of the individual in the system. Okay, all right, so let's come back to the graph. So that is one way of doing the question. So there's actually another way to do the question. The other way to do the question is this. So we can also use M1 D1 equals to M2 D2 using the center of mass equation to find the father's position. Okay, so let's say this. If this is where the center of mass is, so so after the daughter has traveled to here, if the daughter is here, this is where center of mass is. We want to find out, okay, where the father is going to be. Okay, all right, so from here to here, and that is daughter. So daughter is 40, and the distance of daughter to the center of mass, the distance between daughter and center of mass is 4. And then the father is 80, so where the father is going to be, somewhere over here. And then the distance of father, we can calculate that way. In this way, we calculate is 2 meters. So the father should be 2 meters away from the center of mass. So daughter is here, center of mass is here, the father will be over here. And from this way, we can see, the father had traveled 3 meters. So that's why it's 2 meters lagging the center of mass. And the daughter is 4 meters from the center of mass, okay? And which confirms from our answer later is we've calculated the father's speed. It's going to be 3 meters per second, okay? And I can do the same thing to find out using this center of mass. So with this distance, I can find out where the father is. So say I try it again. Okay, m1 d1 equals to m2 d2. Okay, so right now father is still 80 d2. The daughter, where's the daughter now? So this is the center of mass. The daughter is going here now. So let's say that's 8. Okay, so daughter travel 8 and daughter is 40. Okay, so d2 equal that divided by 40. I get 4 meter. Okay, so father should be 4 meter from the center of mass, which is over here. So the father should be over here. As you can see, father traveled another 3 meter. Okay, so it's going to travel another 1, 2, 3. So at the end, the father is going to be over here. So what happened is father go bam, bam, bam. The daughter goes here, here, and here. And then the center of mass is still traveling at the original speed. So that is this question, which is a little bit difficult. So I hope you guys understand that. If there is any question, send me an email and I can help you guys.